Now that we've looked at different methods of charging and charge itself, what I want to talk about is I want to focus in on this aspect of this attraction and repulsion of charges themselves. And the equation that determines how much attraction and repulsion they have is called Coulomb law. Of course, if we're talking about attraction or repulsion, what we're talking about is forces. There's a force that's acting between charged particles. Now, that force could be attractive or repulsive, but when we talk about the force that's acting between two charged particles, we want to be able to define that. And we define that by what's referred to as Coulomb's law. Coulomb's law says that the force between charges is equal to some electrostatic constant K multiplied by the magnitude of the two charges divided by the distance between the two charges themselves. And this is in your reference table. K is the electrostatic constant, and it's equal to 9.0 times 10 to the 9 Newton meter squared per Coulomb squared. When we talk about Coulomb's law, the aspect of Coulomb's law only determines the magnitude of the electric force. Direction must be determined through evaluating whether the charges are the same or opposite. So you can't necessarily take some configuration of charges and identify a direction in which the charges are pushed by positive and negative. So the positive and negative doesn't have a spatial aspect to it. It's either, if it's a negative, what it's telling you is that the objects are attracted to each other. And if your result from Coulomb's law is positive, what it's telling you is that they're repelled by each other. Because if you have two positive charges or two negative charges multiplied by each other, they're going to give you a positive. But if you have positive and negative, you'll get a negative. So you can't use Coulomb's law to tell you whether it's going right, left, up, or down, or whatnot. Only will tell you whether they're repelled or attracted. So it's better just to use Coulomb's law to find the magnitude of the force, and then spatially orient yourself based on whether they're repelled or attracted, and then go from there. These forces are vectors, though. Even though the mathematical value won't tell you whether it's right, left, up, or down, the electric force itself is a vector value. So you'd have to orient yourself spatially and then apply it from there. If you have multiple different charges that are all congregating in the same area and you want to find out how much electric force is acting on one of them, you have to use what's referred to as superposition, meaning that you have to determine the electric force from each charge individually and then add them all up like vectors afterwards. And that is the principle of superposition. Let's do an example of that. Here we have three charges. One on the left, which is 1.5 times 10 to negative 6 coulombs. The one in the middle is 2.3 times 10 to negative 6 coulombs. And the one on the right is a negative 2.2 times 10 to negative 6 coulombs. And what I want to know is what's the net electric force on the 1.5 times 10 to negative 6 coulomb charge. Note that between the 1.5 and the 2.3, the Coulomb, the charge here, is going to feel a repulsive force. But between the 1.5 times 10 to negative 6 and the negative 2.2 times 10 to negative 6, that's going to feel an attractive force. So I'm going to find what the magnitude of the coulombs of the force is between each of these, right? And then I'm going to add them together for the 1.5. So let's go ahead and do that. I'm going to start with the force from Q1, right? So I'm going to do Q1 and Q2, and I'm multiplying 9 times 10 to the 9, that's the electrostatic constant, multiplied by the magnitude of the middle charge, which is 2.3 times 10 to the negative 6, multiplied by the magnitude of the charge in question, which is the 1.5 times 10 to the negative 6. And then I have the distance separating them, which is 2.0 times 10 to the negative 2 meters squared. And what I find is that there's 77.6 newtons between the first and the second charge. Now, this is a repulsive charge, so this first charge is going to feel that pushing to the left. In the second one, we have the same exact idea, except now the rightmost charge is a negative 2.2 times 10 to the negative 6 coulombs, and it has a little bit more distance, 3.5 times 10 to the negative 2 meters. In this scenario, this is going to be an attractive force, pulling it to the right. So the first one is a repulsive force. The second one is an attractive force. Now, to find out how much force is acting on the first object, what I need to do is I need to add the two of them together. which is 77.6 newtons, that's to the left, minus 24.2 newtons, that's to the right. Notice that they don't share a sign because they're acting in different directions, and I get 52.4 newtons. Now that I've found the magnitude of the net electric force, I have to orient myself in there. It's more repelled than it is attractive, and the repelled direction is to the left, so that 53.4 newtons is to the left.